Hey, chemistry, it's really good to be back together with you again in chemistry. As you know, on Mondays and Tuesdays, we're going to do ACT prep, and then Wednesdays and Thursdays, we will do class instruction out of the textbook. So I'm on page 483, but can you go back to page 482? And let's take a look at table 5. You see on page 482, table 5, Arrhenius's definition of an acid and a base is that acids donate protons, they produce protons, and bases produce hydroxide ions. Protons are hydrogen ions, and so here's an acid. What's on the front? When you put it in water, what does it produce? Well, it produces hydronium ions, doesn't it? And it produces chloride ions. Now, Arrhenius says that's an acid because it donates a proton. It releases a proton. It produces a hydrogen ion, or what we call a proton. When there's no electron on the outside of a hydrogen atom, it's called a proton. It's all that's left. And then a hydroxide producer would look like this. Sodium hydroxide, you put that in water, and what you're going to get is sodium ions, and you're going to get hydroxide ions floating around in the water. Okay? And so that's a hydroxide producer, so it's called a base. This is a hydrogen producer, hydrogen ion producer, so it's called an acid. Now, what does Bronsted-Lowry say? It says it's a proton donor. Well, isn't that the same as produces hydrogen ions? Isn't that a proton donor? And it's donating it to what? Well, to that right there. Now, does that species have some what you might call electron pairs that are kind of like lone pairs? Let's take a look at the water molecule. And you've got a hydrogen and an oxygen. And for oxygen, we have 6, let's see, it's group 6. So it's got 6 valence electrons. 1, 2, 3, 4, 5, 6. 2 lone pairs. Hydrogen has 1 electron, 1 electron. There's a shared pair, and 2 lone pairs. And that's what makes water a base. It's because it's got a place where that hydrogen can land. I call it a landing pad. Bronsted-Lowry would get excited about those lone pairs. They'd call it a base because it's a proton acceptor. But Lewis, on page 482 at table 5, Lewis would call water a base because it's an electron pair donor. If it's got these lone pairs, it can donate a lone pair, whatever, over here to the hydrogen. So Bronsted-Lowry is looking this way, and Lewis is looking this way. Bronsted-Lowry is talking about the movement of the positive ion, called the hydrogen ion, and Lewis would look at the negative ion, called the lone pair. And that's the difference in the definitions. Okay, I'm on acid-base reactions, page 483. This whole section 3, the whole section 3 will be talking about Bronsted-Lowry's definition. We're not going to be worried about Lewis's definition, and we're not going to be worried about Arrhenius's definition, just Bronsted-Lowry. And it says that a conjugate base is the species that remains after an acid, a Bronsted-Lowry acid, has given up a proton. What's left is the base of that acid. So we got hydrogen fluoride as the example, or hydrofluoric acid if it's in water, combining with water, liquid, to produce fluoride ion. See, when you strip off the hydrogen, all you have left is a fluoride ion. And the hydrogen takes the positive with it. And that positive connects with the water molecule to create hydronium ions. We say aqueous. We say aqueous. Do you see that? I hope so. And so what's happening here is this. So that's a hydrogen ion positive that's floating on over here and grabbing that. And what's left behind is that fluoride ion negative. Now, if this is an acid, because it donates a hydrogen, then this has got to be a base because it's receiving the hydrogen. If this is an acid, then what's left behind is called a conjugate base. And those two are a married couple. This is what you start with, that's what you finish with. Now, if this is a base, then this will be a conjugate acid. The hydronium ion is the positive. Typically, positive ions are acids and negative ions are bases, but not always. Excuse me. And so we've got this is a married couple. All right. And it's called a conjugate acid base pair. And this is a conjugate acid base pair. And the reason is because when this base gains the proton, it turns into that acid. Now here's the deal. This is a reversible reaction. So is this acid a strong acid or a weak acid? If it's reversible, it sets up equilibrium. It's reversible, it's a weak acid. Hydrofluoric acid is weak. We'll talk about what that means with regard to ionization like this in a little while. Anyway, so if it reverses back on itself, what's happening here is this hydrogen right here, this hydrogen with this positive is going to return to that because they're attracted to one another. And so what you're going to get is hydrogen fluoride back again, and you're going to get a water molecule when it loses a hydrogen. Now, furthermore, we have a way of labeling this. And the way of labeling this is that this is called acid number 1, because it's the first acid you encounter as you read from left to right. So we call it acid number 1, and its associated conjugate base is this right here, base number 1. Therefore, this is the 2's. These are the 2's. That's the base number 2, and that's the acid number 2. They go together, and these go together. And the reason you label this 1 is because it's the first thing you encounter as you're reading from left to right. So now my question is this. Can't remember my question. On the bottom of 483, you see that hydrofluoric acid can go forward and reverse reactions when it's in equilibrium at equal rates. Doesn't mean that the amount of these ions is equal to the amount of these molecules. In fact, quite the opposite. There are more molecules because once it starts to ionize, they come back together again and they reform molecules, so that you might say that this equation lies to the left. That reaction lies to the left. What does that mean? That means that the quantity of molecules is greater than the quantity of the ions. Because there's only a few ions that form, and then all of a sudden it reverses on itself And it sets up such that the rate at which these are being formed is equal to the rate at which those are being formed, except that the rate is the same in which it's exchanging, but there are very few of these and there's a lot of these. Now, equations that go to completion, like for strong acids and strong bases, that means there's only one arrow going to the right, going to completion, all of the molecules turn into ions. Okay. So is it safe to say that last sentence on the bottom of 483, is it safe to say that the acid has one more proton than its conjugate base? The acid has one more proton than its conjugate base. Yes, one more hydrogen positive. Is it safe to say that, oh, by the way, this is what I remember I wanted to say. Would it be safe to say that this is called the conjugate acid? If you want to call that base number one. And if you're talking about going back in this direction. And then you could call this the acid number two, and this would be the conjugate to that acid number two. That'd be the conjugate base, if you're talking about the reverse direction. This is new vocabulary, and that's why you're really all messed up right now, confused and everything else. Look on the top of 484. We're going to talk about the extent of the reaction between a Bronsted-Lowry acid and a base depends upon the relative strengths of the acids and the bases that are involved. So if you look at the equation that they cite, it's hydrochloric acid, which is a strong acid, and that means the water is the base, is going to produce hydronium ions, which is weaker as an acid. Weaker than what? Weaker than the stronger acid, hydrochloric acid. Then the chloride ion is a weaker base. This observation leads to an important conclusion. The stronger an acid is, the weaker its conjugate base. The stronger a base is, the weaker its conjugate acid. Okay, so all you have to identify is one of the reactants or one of the products as either strong or weak. And if you do, you know everything else. What do you mean? I'm going to tell you that this is a weak acid. And in these equations, it's always going to be weak, weak, strong, strong, or it's going to be strong, strong, weak, weak, and never a mixture of the two on one side. So if that's a weak acid, which it is, then this is a weak base, which means that this is a stronger base. What do you mean stronger base? It's a stronger base than the water. And this is a stronger acid. Stronger acid than what? Well, then this acid over here. Well, I thought that that went with the base. Well, yeah, I know that's a conjugate acid-base pair, but when you compare the strength of it, you got to compare the acid with the acid. Okay, so it's either going to be weak, weak, strong, strong, or strong, strong, weak, weak. Well, how do you know? Well, look at the table on page 485 and you can figure it out. Let's take a look at this. Find hydrofluoric acid. Find hydrofluoric acid, HF, on table 6, page 485. You see where it is? Now, go up and look at the acids that have the asterisk next to their name. What does the asterisk mean? If you look at the bottom right-hand corner, way down here, you're going to see that the asterisk means the strong acids are these right here. Because they got the asterisk next to them. And it says increasing acid strength goes up. So that means hydrofluoric acid is a weak acid. Anything that doesn't have an asterisk is a weak acid. It's certainly weaker than the other acid. Right? The hydronium ion is up here. and hydrofluoric acid is down there. And so it's weaker. Well, now let's compare the bases. The fluoride ion is a stronger base than water. Find the fluoride ion on here. There it is right there. And the bases get stronger as you go down. So the fluoride ion is stronger than, further down, than water. Fluoride ion is further down. It's stronger than water. See that arrow right there? The strength gets stronger going down that way for the bases. Strength gets stronger going up this way for the acids. Now you can compare things. Now you know which ones the strong acids and strong bases are. The strongest bases are the ones down here. These bottom three are really strong bases. Otherwise, they're weak bases. And then you can compare them based on their relative position on the table. I'm going to read one more thing, and then we'll pick up here tomorrow. Look on the bottom of 484. Bottom of 484, the italicized words, right down here. Okay, it says, proton transfer reactions favor the production of the weaker acid and the weaker base. So which is the dominant direction? Is it going to the right or is it coming back to the left? Well, it says that it favors weaker stuff. So it's always blowing in this direction for that reaction. So it is going like this because the haves are given to the have-nots. See ya.